Superconductors are materials that conduct electricity with zero resistance below a certain temperature, called the critical temperature or TC. They have numerous applications in modern technology, from medical imaging and particle accelerators to power transmission and levitating trains. Understanding the chemistry of superconductors is crucial for unlocking their full potential and developing more efficient and sustainable technologies. They're conventional or low-temperature superconductors and high-temperature superconductors. The former typically have TC below -230 C and are made of pure metals and metal alloys such as mercury, lead, niobium, and titanium. They rely on the principle of electron pairing to overcome the resistance caused by atomic vibrations, known as phonons. When electrons pair up, they form a superconducting condensate that behaves as a single entity, allowing electricity to flow freely. However, this requires extremely low temperatures and strong magnetic fields, which limit their practical use. High-temperature superconductors, on the other hand, have TC above -100 C and are made of complex ceramic compounds such as cuprates, iron pnictides, and hydrides. They exhibit similar electron pairing, but their mechanism is more mysterious and less understood. Instead of phonons, they seem to rely on other interactions, such as magnetic fluctuations, charge density waves, and spin excitations. This makes them more versatile and promising for various applications, but also more challenging to synthesize and optimize. One of the key factors that determine the properties of superconductors is the crystal structure, or arrangement of atoms, in their lattice. This determines the distance and angle between adjacent atoms, which affect the strength of the electron-phonon coupling and the coherence of the superconducting condensate. For instance, cuprates have a layered and distorted structure that creates strong electronic correlations and anisotropic transport. This leads to various phenomena, such as pseudogaps, vortices, and stripes, that are still not fully understood. Another factor that influences the properties of superconductors is the doping level, or the amount of impurities or foreign atoms introduced into the lattice. This can either enhance or suppress the superconductivity depending on the type and location of the dopants. For instance, doping cuprates with oxygen or strontium can increase the TC and the critical current density, while doping them with zinc or copper can reduce them. This is because the dopants affect the density of charge carriers and the symmetry of the crystal field, which affects the lattice vibrations and the electron pairing. Yet another factor that affects the performance of superconductors is the fabrication method, or the way in which they are synthesized and processed into usable forms. This can involve various techniques, such as solid-state reaction, melt processing, chemical vapor deposition, and pulse laser deposition. These methods affect the microstructure, morphology, and composition of the superconductors, which can alter their transport, magnetic, and thermal properties. For instance, the use of nanoscale grains, thin films, or coated conductors can increase the surface area and reduce the grain boundaries, which leads to higher critical currents and lower losses. Despite the challenges and mysteries, superconductors hold immense promise for the future of science and technology. They can enable faster, cheaper, and greener energy transmission, storage, and conversion, as well as more sensitive and precise medical and scientific instruments, and more powerful and efficient particle accelerators and fusion reactors. By advancing the chemistry of superconductors, we can unlock their full potential and create a better and brighter future for all.